Okay, so in today's video I am going to introduce a new topic in white box testing, that is called the data flow coverage. So far we just talked about structural coverage of different graph elements, which was extracted for a piece of code in terms of what parts of the graph was covered by different test parts with respect to some specific test coverage criterion. For example, we wanted to cover nodes, we wanted to cover some edges, and we wanted to cover some edge pairs, simple parts, prime parts, and so on. And we also talked about round trip parts in that structural coverage of the graph context. So now we will be using a somewhat different kind of a graph, which will be also similar to the graph we have just seen in the previous videos, but this graph will contain the definitions and uses of data elements which are there in any software code. So what do we mean by that? Is that we are interested to know what definitions of variables and what are the uses of variables, and which definitions of a variable go to a specific use of that variable. And this can be quite significant because sometimes there are branches in the code, sometimes there are conditions in the code, and we might be interested to see whether a particular definition reaches a specific use where it was intended to be used. So in that context, data flow coverage is very important, and we need to carefully analyze the graph in terms of how data is defined and how data is being used in the graph. So the goal of data flow coverage is to find out or ensure that values are computed and used correctly. So in this context, it is necessary to know what is a definition. What do we mean by a definition, or simply stated as def in this context? A location where a value for a specific variable is stored into memory. And in the same context, what do we mean by a use? A location where a variable's value is assessed. So this location basically is on the graph, which we will extract from the code by maybe some tool, and we will be identifying the locations in the graph where a specific variable is defined and where that particular variable is being used in the graph. So for example, here we have this simple graph, and what difference you see in this graph compared to the earlier graphs we have seen is, here we have these declarations and uses, or definitions and uses of some variables, and these are not absent in the CFGs we have studied so far. So in technical terms, we say that the graph has been annotated. Annotated with what? With definitions and uses of data. So in this context, on node 1 we have defined the variable x to have value 42, and in the same way at node 5 variable x is being used, and variable z is getting the value of x times 2. On node 6, variable x is again being used. It was defined on a previous node, some earlier node. It is being subtracted, and this new value is being stored into a variable called z. So here the variable z is being defined and the variable x is being used, and the same is the case with node 5. Here variable x is being used and variable z is being defined, or it is being given a new value. So we use these notations, defs. So when I use a definition def of 1, it means which variables are being defined at node 1. So it is variable x. When I say def of 5, it means which variable is being defined at node 5. So it is z. You can see it from here. And when I say def of 6, what does that mean? It means which variable is being defined at node 6. So you can see is this variable on the left of the assignment operator. This is variable z. So again I can write z in this one. So again the new notation for use is, when I say use of 5, so which variables are being used at node 5. So here you can see it is the variable x that is being used, and which variable is being used at node 6. So here again you can see from this graph or annotated graph that this is variable x. So this annotated graph is also called DFG. So what does it stand for? It stands for a data flow graph. So this is how these different uses and definitions are given on a graph. So the values given in defs should reach at least one, some, or all possible uses. So whatever variable is being defined in the code, which visibly reflected on the data flow graph, the goal is to have this definition reach at least one, some, or all possible uses of this variable. So based on these three concepts, there are two or three different data flow coverage criteria which software testers need to focus. So we have some other definitions. First one is of a due pair, and then of a due path. So for this we need to think about what is meant by def of n or def of e. The set of variables that are defined by node n that can be notated with def of n, and if there are some variables that are defined on an edge e, those can be notated with def of e. And likewise you can say use of n or use of e. So what does that mean? The set of variables that are used by node n or edge e. So if some variables are being used at node n, then we can use this notation use of n or use n, and if those variables are being used at an edge, then we can say, or we can use this notation use e. So the another important definition is of a due pair. A pair of locations li and lj such that a variable v is defined at the first location li and it is used at location lj. So this definition is in the context of a variable. Let's call that variable v, and if it is defined at some location li and it is being used at a location lj, then we call this pair of locations as a due pair. So the next definition is of a def clear. A path. A def clear path is a path from location li to location lj with respect to some variable v if v is not given another value in any of the nodes or edges in the path. So for example, if I have this variable having some value here and we pass along a certain set of nodes, and let's say it gets used here, and if v does not get any new definitions on these subsequent nodes, then we will say that the path from this node, let's say this is 1 and this is n, so this path is a def clear path. If however this v gets another definition, for example here let's say I or something, then this path from 1 to n will not be considered as a def clear path with respect to v. So it must not have any subsequent new definition after this node till that node where it is being used. If that is the case, then we call this a def clear path. So another definition is of reach. If there is a def clear path from location li to location lj with respect to this variable v, then we say the def of v at li reaches the use at lj. So if we have this again simple graph, let's say v was having some value here, any value, let's say it's a, and then x gets this value, then and we don't have any subsequent definitions here, no definition, let's cross this, then we say that this path from here to this node n, for example, this is a def clear path. So what is then a simple a due path? A simple subpath that is def clear with respect to a variable v from a definition of v to a use of v. So a due path is also a simple means there are no duplicate or repeating internal nodes. So the simple definition of simple subpath will remain the same which we studied in earlier videos. So it will not have any repeating internal nodes, and it must also be def clear with the definition with respect to some variable, and then we would say that this is a due path from a def of v to the use of this particular variable v. So we have two different notations. One of them is due ni, nj and v. Here we specify the starting node, we also specify the ending node. So these are not necessarily the start or initial or the final nodes of the graph. These we are just talking about in the context of this variable v. So if this variable has some definition of ni, and we want to see whether there is any use of v on the parts that go from ni to nj, then we would say that this is a if it is a def clear path, or there are multiple parts that go from ni to nj with respect to v, then we will call all those due parts to be def clear, and we will retrieve that set with this notation. If I write this due ni, nj and v with respect to v, it means fetch me all those due parts that start at node ni and end at node nj with respect to v. So if it is one path or more parts, all those will be retrieved when we use this notation or call this function. And then the second one is we just give the starting node ni and we give the variable under consideration. So in this case we just are telling this function to consider variable v and this specific node ni and see whether there are any due parts that start from node ni. If there are some parts, then fetch those parts, and those will be our desired parts. So Turing due parts. So this is not that definition of detour or d. So this is a bit different. So now we are using the word due. It's not d, which we studied earlier in the context of control flow graphs. So when we talk about due tour or due parts, then it means def use. We are considering the def uses of variables. So a test path, again the definition will remain the same for the test path. A test path is a path that begins at the initial node of the graph and always ends on the final node of the graph. So a test path B due towards, so now we are not talking about D, it's a due toward, it means def use towards subpath D with respect to some variable V if P towards D and the subpath taken is def clear with respect to V. So if the test path is touring this D and the path taken, subpath taken is def clear with respect to V, then we say that this test path is due touring that particular subpath. And the side trips can be used as we studied earlier. It means if this test path leaves this subpath at a specific node and then comes back onto the same node from where it left the subpath, then we would call that this was a due tour with a side trip. So we have three very interesting coverage criteria for data definitions and uses. First one is use every def, then is get to every use, and then is to follow all due parts. So let's see these one by one. So first we make sure every def reaches a use. So this means all defs coverage, and it is abbreviated as ADC, and for each set of due parts S is equal to due NV. So here we just give the node and the variable. And what do we mean? That all due parts that initiate at node N for this variable V, and we don't mind wherever whatever node they end, this function is supposed to return all those due parts. And what is the test requirement in this case? Test requirement contains at least one path D in S. So if there are more than one due parts starting at node N with respect to variable V, so all defs coverage mean we just need to cover one definition. So definition is at node N. So if we take any one of those definition, any one of those paths, it will take us from this definition to a specific use of this variable. So therefore the definition of this variable will be covered. So in this case just one path is enough to cover or to provide us the all defs coverage. So then we make sure that every def reaches all possible uses. So in this case we notated this because we are also interested that a specific definition on this node reaches a specific use on this node. It is possible that from this node to get from this node to this node there are two different paths. So for each set of due parts to uses S, test requirement contains at least one part D in S. So if there is a path from one use, one definition of the variable, a definition of a variable on Ni to Nj, and for example there are two parts, so but this is just one use on this node, so it is enough that we cover at least one of those two parts. So in that case we are also mentioning that we want to get to that use of this variable corresponding to this definition that is given on node Ni. So if there are one or more than one parts, we just need to write one part to ensure that we have covered this use of the variable which is given on node Nj. And the last one is all the parts between defs and uses. So that is termed as all due parts coverage, and for each set S is equal to due Ni Nj V. V is the variable which we are considering. Tr contains every path D in S. So in this case we are also telling the initial node where this variable is defined. It is possible, let's say, that there are more than one path that go from this definition at Ni to node Nj. So all due parts coverage means we have to consider, or we have to retrieve all those parts that are def clear for a definition of variable V at node Ni, and we go to node Nj. So let's clarify this more on the next slide with an example. So here we have a definition of X on node 1, use of X on node 5, and a definition of Z, and we also have a use of X on node 6, and here we also have a new definition of Z. So in the all defs coverage, we said we just considered a node where a variable is defined, and since we want to cover the def, So we are interested in all those due parts which can be retrieved by this function with that that start a node ni with respect to variable v. But if we take only one path, then that will be enough to achieve all defs coverage. So here the definition is here, and the uses are on this path, on this path, on this path, and on this path. But the definition is suggesting me that I just need to consider this node and any of these 4 parts. So I, for example, can write that the path 1, 2, 4, and 5. So one node, the first node, node 1, has the definition of x. So if I am talking about all defs coverage, so out of these all 4, I can just pick one, and that will be enough to cover all defs coverage. So it provides me the definition which is on this node. So I have covered the definition of x which was on node 1. And what was the case of all uses? For each set of due parts to the uses, we specify the node, initial node, where the variable is defined, and we also think about where a variable is being used. So let's see how we can do, and we need to cover each path that take us to a different use. So let me erase all the ink in this case so that it becomes a little bit clearer. So now I can also change the color of the pen. For example, I have one path which take me to this use. I have another path which take me to this use. Then I have a path that take me to this use, and then I have a path that take me to this use. So I have 4 due parts, and I want to get to all the uses. And if I think about this, the top one, I can get here by means of this 1, 2, 4, 5 and 1, 3, 4, 5. So it is enough to write just one of these. For example, if I write 1, 2, 4, 5 and I skip 1, 3, 4, 5, so I am covering the use of x at node 5. I don't need to write both these paths. I have covered this use by this path. Similarly, now I want to cover this use of x. I have 2 possibilities. Either I take this path 1, 2, 4, 6, or I take this path 1, 3, 4, 6. I can write any one of these. Let's say we write 1, 3, 4, and 6. So this is enough for all uses coverage. And what happens in the case of all due parts coverage? So here we cannot leave out any due parts. Whatever due parts are there that take us from this definition of x to the uses of x, we need to write all of those. So let's make use of the eraser and clear this, and now we can write again. So in this case I have to write 1, 2, 4, 5, 1, 2, 4, and 6. Then is 1, 3, 4, 5, and then 1, 3, 4, and 6. So these parts which take us from the definition to a use of x, and these form due parts for the variable x on this graph. These all will have to be written to achieve all due parts coverage for variable x on this particular graph. So this is now elaborated on the slide by means of these animations. So far we studied about these different sorts of coverages. We talked about node coverage, and we talked about that node coverage is subsumed by edge coverage, and edge coverage is subsumed by edge pair coverage, and all defs coverage is subsumed by all users coverage, and all users coverage is subsumed by all due parts coverage. In the same way, complete round trip coverage subsumes the simple round trip coverage, and The prime path coverage basically subsumes both these coverages, and complete path coverage subsumes the prime path coverage, and it also subsumes this H pair coverage. And we also found out that prime path coverage does not subsume H pair coverage because of some special cases when we have these kind of loop on a graph, for example 0 and 1. Now 0 1 1 is a valid H pair, but this does not form a prime path, so it means and all the H pairs cannot be covered by the prime path criteria. So therefore prime path coverage actually subsumes the H coverage criteria. So this was all about the simple graph, structural graph coverage and data flow graph coverage, and in the next video I will provide you a demo of data flow coverage web application. So till then, thank you very much.